Bismillah, this is Dr. Magda Talib Al-Hinai from the Department of Mathematics and Statistics presenting functions operations. This presentation is exclusive for the Independent Learning Center at Sultan Qaboos University. Suppose we have a function f whose domain is df and a function g whose domain is dg. We can define four new functions defined on their domains by adding, subtracting, multiplying, and dividing the functions f and g. So let's have a look at this table. We have in the beginning f plus g of x. This is equal to f of x plus g of x. The domain of this new function is the set of all real numbers on which both f and g are defined. And here the word "and" means the intersection of df and dg. The second function is the difference between the two functions f and g. So f minus g of x is equal to f of x minus g of x. Also here, the domain of this new function is the intersection of the two domains df and dg. For multiplication, we have f times g of x is equal to f of x times g of x. Also, the domain of this function is the intersection of the two domains df and dg. The fourth function is f divided by g of x. This is equal to f of x divided by g of x. The domain of this function is the intersection of the two domains df and dg. But here we have to add one more condition, which is the denominator should never be equal to 0, meaning the domain of this new function is df intersection dg and g of x is not equal to 0. Here we have an example. Given a function f of x is equal to square root of x and g of x is equal to x minus 1. We are asked to find f plus g of x, f minus g of x, f times g of x, and f divided by g of x. So first we have to find the domain of each function, the domain of f and the domain of g, and then we will find the intersection of the two domains. So let's start by f of x. Here we have f of x to be square root of x. So what's the domain of square root of x? Yes, the domain of square root of x is the set of all real numbers which makes what's under the root greater than or equal to 0. So here we have df equals the set of all x such that x is greater than or equal to 0. Okay, what about g of x? As we all see, g of x is equal to x minus 1, which is a polynomial of degree 1. And for any polynomial, the domain is the set of all real numbers. So now we start finding the intersection of df and dg. As we see in front of us, the intersection is the set of all real numbers x such that x is greater than or equal to 0. Now we find the sum. F plus g of x is equal to f of x plus g of x, which is equal to square root of x plus x minus 1. This is defined on the intersection of domain of f and domain of g, which is equal to the set of all real numbers x such that x is greater than or equal to 0. Next, we go to the difference. F minus g of x, this is equal to f of x minus g of x, equals square root of x minus 1. Now we open the brackets, so we have square root of x minus minus 1 is plus 1. And also this is defined on df intersection dg. Now we go to the multiplication. F times g of x, this is equal to f of x times g of x. This is equal to square root of x times x minus 1. Now we distribute the square root of x inside the bracket, so we have x square root of x minus square root of x. Also, this function is defined on df intersection dg. Finally, we go to f divided by g of x. This is equal to f of x divided by g of x, which is equal to square root of x divided by x minus 1. Okay, here we notice that the domain is the intersection of the two domains such that the denominator is not 0. So The domain of this function f divided by g is the set of all real numbers x such that x is greater than or equal to 0 and x is not 1. So here we have another example. Given f of x is equal to 1 over x minus 25 and g of x is equal to square root of x minus 2. Find f plus g of x, f minus g of x, f times g of x, and f divided by g of x at x equal to 27. As we did in the previous example, we will find the domain of f and the domain of g, and then we find the intersection of the two domains df and dg. So the domain of f, as we see, is the set of all numbers except what makes the denominator equal to 0. So df is equal to the set of x such that x is not equal to 25. And for dg, we have the domain of the square root of x minus 2. As we know, the domain is the set of all real numbers which will make what's under the root greater than or equal to 0. So dg is equal to the set of x such that x minus 2 is greater than or equal to 0, meaning that dg, domain of g, is equal to the set of all real number x such that x is greater than or equal to 2. Now we'll find the intersection. So the intersection of df, which is in front of us, the set of all real numbers x such that x is not 25, with dg, which is the set of all real numbers such that x is greater than or equal to 2. We make the intersections of these two sets so that we will have the new domain to be the set of all real numbers x greater than 2 and x is not 25. And in front of us we see the diagrams on the right hand side. I give df the red color and I give dg in the second line the blue color, and then I make an intersection of the two domains. So I get the purple color, mixing blue and red will give you a purple, and here we have df intersection with dg as in front of us in the third line. Now we need to evaluate f plus g of x at 27. So first we find f plus g of x and then we plug in the 27. So f plus g of x is equal to f of x plus g of x. This is equal to 1 over x minus 25 plus square root of x minus 2. And we plug in the 27 for each x. So we get 1 over 27 minus 25, this is 1 over 2, plus square root of 27 minus 2, which is square root of 25, this is 5. So we have half plus 5, this is 11 over 2. Now for the difference, f minus g of x is equal to f of x minus g of x. As we see, we substitute for f of x, I have 1 over x minus 25 minus g of x, which is minus square root of x minus 2. Again, we plug in the 27 for each x, we arrive at f minus g of 27 equal to minus 9 over 2. Next, we find f times g of x. This is equal to f of x times g of x. We multiply the two functions, 1 over x minus 25 times square root of x minus 2. And we substitute for each x by 27, so we get square root of x minus 2 will be square root of 27 minus 2 in the numerator, while in the denominator we have x minus 25 substituting for 27, so we have in the denominator 27 minus 25, we arrive at f times g of 27, this is equal to 5 over 2. Finally, we calculate the f over g of x at x equal to 27. So f over g of x, this is equal to f of x divided by g of x. This is equal to 1 over x minus 25 multiplied by square root of x minus 2 in the denominator. Now we substitute for x equal to 27, we get f over g of 27, this is equal to 1 over 10. After we finish the discussion of forming new functions from two functions f and g by adding, subtracting, multiplying, and dividing these two functions, we will move on to composite functions. Suppose we have a function f whose domain is df and a function g whose domain is dg. The composition of the function g with the function f is given by f circle g of x. This is equal to f of g of x. So we see a diagram in front of us, a set which is in blue color, having an element x. The function g will take the x to the g of x in the green set, and then the function f will take the g of x to f of g of x. So we have two steps, g taking x to g of x, and then f taking g of x to f of g of x. We can do this in one step by using the composite function f circle g of x as we see in front of us. And as usual, whenever we define a function, we have to know the domain of this function. So the domain of composite functions is simply the set of all values x for g to be defined, provided that g of x itself is in the domain of the function f. Here we have an example. We have a function f of x equals to 2x squared and a function g of x equals to square root of 2 minus x. We are asked to find f circle g of 2 and g circle f of 2. So we start with part A, finding f circle g of x, which is f of g of x. The function f takes the element to its square and then it multiplies it by 2. So the function f will take g to the square to g squared, and then it will multiply it by 2. So f of g of x is equal to square root of 2 minus x all squared multiplied by 2. This is simply 2 times, open bracket, 2 minus x. Now, when I substitute for x equals 2, we find f circle g of 2. This is equal to 0. Now part B, find g circle f of x, which is g of f of x. This is equal to square root of 2 minus f of x, which is square root of 2 minus 2x squared. Now we evaluate g circle f of 2. This is equal to square root of 2 minus 2 times 2 squared, which is equal to square root of 2 minus 8. As we see, this is square root of minus 6. So g circle f of 2 is equal to square root of minus 6, which is undefined, meaning that 2 itself is not in the domain of the function g circle f of x.